several books also. For example, one book by Ifra on Universal History of Numbers actually says the scale at which the atoms were proposed was something like what in the modern day we call as about 2.9 angstroms. So you can see the kind of depth at which they have tried to understand the concept of atoms, and then they proposed. And of course, more or less simultaneously, Democritus proposed it in Greece, the concept of atom. Now, both are being acknowledged as the first, to propose the principles of atom. But in the modern day, we all know about John Dalton's, atomic theory, and also the later on, after the birth of quantum physics started, the Ernest Rutherford's experiment of identifying the constituent of atoms, especially the nucleus, where with this alpha ray experiment, he showed that the recoil is due to the nucleus. And then his student Niels Bohr proposed what is more or less accepted as the starting point of the modern theory of modern structure of atoms. So this is how it started evolving. The question generally may ask, why don't we use more and more powerful microscopes, optical microscopes, to really see the atoms and molecules? Because you can always improve the power of the lenses, and then perfection of the lenses, and then be able to see smaller and smaller matter. So, but there is always a limitation, because you are trying to see something much tinier than the wavelength of light. So the wavelength of light typically extends from 400 nanometers to 800 nanometers. So you want to see something like sub nanometer size. So obviously you can't really be able to see something much smaller than the tool with which you want to probe. So that is the limitation of light. And one of the important properties which actually limits the resolution is the well-known diffraction, interference, and diffraction. So the famous double slit experiment of Thomas Young has shown that you will not be able to get the clear pointed images when the light is passed through two double slit, two slits, adjacent slits. You will always end up with an interference pattern like this. So in order to resolve, you need to have a very clear separation of two different objects. That is, this is how it will be well resolved. But if it is merging together, there is a partial, resolution. And when they are together, completely merged, then this is unresolved. So this kind of image will not be able to give you the correct, the particle size and particle dimensions. So this is actually, the limitation is very well documented, and this is called a Abbe's limit. That is the resolution limit. Is if it is a delta, D, that's the separation between the two point sources, then it is given by lambda by 2 mu. Mu is this, refractive index, and theta is this cone angle. So you can, if you really want to increase the resolution limit, you need to really have a very, very small wavelength, and that is the, close to violet, in terms of optical region. And that actually, roughly this is lambda by 2. That really makes it the resolution possible even with a perfect lens, which is not really, realistic. In any ideal lens is not possible. So however much you try to make a perfect lens, there are, but even with a perfect lens, theoretical limit is something like 0.29 micrometer. So to see an atom of angstrom sizes, angstrom is, 1/10 of a nanometer, it is necessary to attain a resolution something like 3,000 times higher. So, in the electromagnetic radiation, you have much lower wavelengths also. So you can one can try, for example, X-ray. And in fact, electron beam itself is something which has very low wavelength, very high frequency. So can we use electrons as probes? This is electrons, was something demonstrated with the cathode ray experiment by Joseph Thomson. And these electrons as a source has been used in scanning electron microscope. So this is something which extends the resolution of optical microscope to much higher level. See, the electron microscopes, you have scanning electron microscope, and also you have the transmission electron microscope. I'm not going to go too much details into these things, but scanning electron microscope is an excellent instrument, and it is something, a workhorse of many laboratories to really see the, images of samples, mostly conducting samples. Now, there are many ways in which you can also see non-conducting sample, what's called charge-coupled mode and other things. But these are all, highly specialized advancements. But classically, scanning electron microscopes, you can use only for conducting samples because of the very high energy electron beam, which is, getting impinged on the any surface. So that you can get a resolution typically of the order of some 1 to 10 nanometers. So that's good enough. And most of the SEMs are used for fracture analysis and in metallurgical applications. And transmission electron microscope can go to much higher resolution. And this is nowadays being used mostly to study the nanomaterials and nanoparticles, but there are demonstrations of visualizing the atoms using SEM and TM, but they are only to show a proof of the concept. But they cannot be routinely used for such studies, as limitations like using ultra high vacuum, and it doesn't really provide a 3D image. We are talking about studying the surfaces, because surfaces are very important, just as important, or if not more important than the bulk properties, because surface properties are something that defines many other functionalities. For example, many of the catalysts that which is being used in the chemical industries, they all depend on the surface properties. That's where the adsorption, desorption, and all those things. This is all mostly heterogeneous catalysis. So that's what is it. And the surface properties in terms of studying the thin films, monolayers and other things, they are all something which are very important, and the surface properties play a very important role. So surface studies are something that really needs to be studied in greater detail for many of the technological advancements. So after this SEM, which was actually ruling for quite 2 or 3 decades, then came scanning tunneling microscope, which is based on the quantum physics principle. As I said, one of the important outcomes of quantum physics is the scanning tunneling microscope, even though earlier scanning electron microscope and many other devices like, tunnel diodes and other things had taken place. This is the one instrument which has really revolutionized the study of the surfaces. So I was just telling about the electron wave. The question is, how do you explain the phenomena of tunneling before we understand scanning tunneling microscope? So the electrons, is just like light. You can say light is a photon, it's a particle, as well as an electromagnetic wave, but both are the same. It's only the way in which for example, photoelectric effect, where it shows photon as particle, and then diffraction interference shows as as a wave. Same way, electrons are also they also exhibit the properties of particle and wave. And this phenomena is being used in scanning tunneling microscope, because tunneling property itself is a offshoot of the quantum physics principle, where the particle is, or wave is, described in terms of wave function. And the author of this wave function is Erwin Schrödinger, who actually is also, one can say, father of second generation quantum mechanics, along with Heisenberg and Louis de Broglie. And he is also a great admirer of, philosophy, Indian philosophy. So the very concept of quantum mechanics itself leads one to think about, philosophy. So all of them, Heisenberg, Niels Bohr, so they all were interested in, they also written books on Indian philosophy. So the concept of wave function itself has multiple interpretations. I'm not going to go into that. But then one can actually say the wave function, the square of the wave function actually defines what's called probability density function of the existence of particle at a particular position. And Heisenberg has come out with the, uncertainty principle, where if you define the, if you can find out the position precisely, then the momentum is, undefined, and the vice versa. So this is a concept which also is reflected in de Broglie's equation, where the wavelength is given by Planck's constant h divided by mv. So for a small particles like electrons, protons, if you substitute the value of m, they have certain wavelength. And of course, you can substitute anything. And if you substitute 70 kg human being, you will have a wavelength of 10 to the power of minus 37 or something like that meters. So the meaningful value of the wavelength is obtained. That is measurable, scale of wavelength. You can actually find out with the subatomic particles. So the electrons show this kind of a phenomena, and this is the famous Schrödinger equation. And a solution for Schrödinger equation for what is called a particle in a box. This is a potential well, where the particle exists. In this case, let us say an electron, and it has the zero potential energy, and it has to cross a barrier of potential energy V0. Classically, this is forbidden, just like, this is a frictionless carriage, which can actually surmount this barrier. But you can't expect with this potential energy to cross this barrier, because this is much higher. Even if it is frictionless, it will stop here. So, but this is the classical situation. In a quantum situation, this can actually cross this barrier and go to the other side. That is the beauty of quantum mechanics, and that is the beauty of Schrödinger's wave equation, and that is the way. This is Heisenberg uncertainty principle is also. So as there is a finite chance that this, the electron wave can also present, the other side of the barrier. Suppose if you, think that this is, a metal piece, and this is another metal piece, and what is it that is actually separating these two metal pieces when they are not in contact? This is the barrier, which we call as work function. So you recall the photoelectric, effect, where the photons, unless they have certain energy, however much the intensity, your electrons cannot be ejected. So that energy that you are actually applying is what is called a work function. This work function is the barrier, but even without any intervention, there is a finite chance that the electrons are existing even just on the surface, on the free surface, above the metallic surface, and that region is extending to the other metal. So there is a crossover, the electron can cross from one, metal to the other metal, even though there is a small gap. The gap is typically of the order of a nanometer. So if that is the kind of gap, you need not have to touch. And if you apply a sort of bias voltage, the Fermi levels of a tip and a sample, and when you apply a bias voltage, the electrons can jump from the sample to the tip. And if you apply the other, polarity of the bias, it can jump from tip to the sample. So this, though there is a vacuum gap. So this is actually the wave function decays exponentially with the distance. And this is the outcome of the solution to Schrödinger wave equation on a particle in a box situation. So this is the tip, and see, you can actually have electrons not just confined to the atoms, but just they are also present away from the surface, and the electrons of the substance, substrate. So this is the surface if you are studying, and you have a tip like this, and you can see there is an overlap of the electrons here, electrons of the tip and electrons sample. So all that one needs is very, very sharp tip like this. This tip has to be very rigid. So it can be something like tungsten, which is my favorite one. Or it can be because it's very rigid, and you can't really easily bend it. It's not a ductile like platinum, iridium, platinum, rhodium is also used, but it's more ductile. So this is the kind of tip you can actually use. And when you just use this, scan this tip over a surface, you will find the gap distance between the sample and tip changes as the tip hovers over the surface. Okay, so this is regarding the invention of the scanning tunneling microscope. This was invented by Gerd Winning and Henrik Rohrer at the IBM Zurich laboratory in 1981, and they won the Nobel Prize in 1986. Though it has really created waves afterwards, you can see the humble picture of a surface, what's called a silicon 7x7 reconstruction. So this is a geometric pattern of a single crystal of silicon. Let's not worry about it. But then they used a very, novel kind of mechanism to really make the tip to scan over the surface. And in those days, we didn't have all those, devices, for imaging and all those things. So they used our humble X-ray recorder, and then they made a wooden relief like this. So this is the one which actually changed the entire concept of looking at atoms. So these are all silicon atoms. You can see though they were deprived of whatever we are enjoying today, they could somehow struggle to, manage to bring out the surface atoms in that, with the simple, ink recorders, X-ray recorders. Many of the people, younger generation, would not have seen it. And this is something that was, workhorse of many laboratories in plotting the graphs and all those things. So this is the one, and you can see this is how it acts. There are two modes in which it actually operates. What's called constant current. Now I told you the tunneling current between the tip and the sample is actually proportional to the distance. So there are two ways in which actually you can make the tip scan the surface. Now you can see there is a, the atom is positioned here. In between two atoms, there is a depression. So one has to really scan the surface in such a way that it is able to really, make out where the atom is there, and then the gap between the two atoms. So either it can be done in two ways. The tip can be brought to, close to the surface, and there is a current. And then as here, the current decreases because the distance increases. But one can actually, what is called a feedback mechanism, by means of which you can actually measure the current and then convert it into voltage, how much it differs, and then you apply that feedback to that, so that it actually goes towards the sample, depression. And, so that way you are actually, making the current constant, because the gap separation is constant. So that way you can do it. This is the common mode in which surfaces are scanned. There's another mode called constant height mode, where the tip is actually scanned irrespective of the surface, profile. That is, it is just scanned in a plane. And as you scan, the current is more here, current is less here, current is more, current is. But this mode is operated only with atomically smooth surface. If it is a somewhat rough, what happens? The tip will touch the surface at one point, and the tip will get, blunted. So this is how so this is called as, this is a feedback loop, constant current, and this constant height mode, where there is no change in the. So the entire block diagram of this is, see, how do you really manage to bring the tip and sample at a distance of 1 nanometer? So this is a very challenging one. You can't really use, motors and other things, because there are a lot of limitations. Even in the best motors, you can get some, you can get something like 100 nanometers or so kind of resolution. But if you use a piezoelectric piezoelectric materials are somewhat, they have which is very common in our kitchens also, where you just press the lighter, and then immediately spark comes. So here you are applying a pressure and producing the voltage, and that voltage produces the, spark. Now it actually works the other way. Now you apply a voltage, and then it actually stretches and compresses. So this piezo material, and to which you have attached a tip, and this tip actually, you can actually move it, So the idea of using a piezo material is, these piezo materials have excellent resolution. That is, even for millivolts, it will be able to move, a few angstroms or something like that. And you have a tunnel current is amplified, and then you have feedback, all those things. I don't want to go into those details. So it is a 4-quadrant piezo. See, you have to scan it in X and Y directions. So to move X direction, you use 2 opposite quadrants, and a Y direction, another 2 opposite quadrants. You apply suitable, sawtooth waveforms and triangular waveforms in order to, so this is the kind of thing which we used in RRI. So piezo displacement, you can see, if you apply 1 volt, it moves by 5.8 nanometer, means you can see the kind of resolution. You want a sub-nanometer resolution. So let us say something like 100 times less, means if you apply some 10 millivolts, it will be. So 10 millivolts is a very realizable value, So you will be in a position to control the piezo and manage to. So this is the one which we used at RRI, and this is a sample holder. And the sample holder is a split copper, small cylindrical device, and in which you have there's 2. It's a spring. There is a pin here. There are 2 pins and a spring loaded, and this is the one which is, and they have a ball bearing, and this is a sample holder. So these 2 ball bearings, there are 2 ball bearings there also. It is just inserted into a tube, like this. And then you have this, graphite, sample here, and you can see the tip here. This is a tungsten wire. I said you can sharpen it by electrochemical means, by dissolution. And so these are the ones. So this is the first STM which we have. Don't be thinking that this is the STM. This is the scanner. But you need a much more elaborate, electronic components and electronic instrumentation for control and other things. So, so this is the kind of thing, so with that kind of thing, you can actually bring the sample close to the tip, but it should not touch the tip. That's the important criteria. So it has to come and stop at 1 nanometer. This is the most challenging aspect, which was really, very difficult. But the way it moves is you don't need all the stepper motors and other things. It simply operates by what's called a friction and inertia. So when you're slowly compressing the, piezo, the glass is brought forward, and then along with that, the sample holder. So this is slow. And when you release it, the glass tube goes back, but the sample holder remains there because of inertia. So like that, in individual steps, you can bring it here. And as soon as it detects the tunneling current, your feedback is applied, and then, and in order to move, this is for Z movement. And in order to move in the X and Y direction, you need to simply bend it. You apply voltages to the opposite quadrants. So you can actually, let us say it is in some Y position, and you scan it in the X, several points you can take, and then you can retract. That is, so it will produce a mirror image of the sample. So this is the, one which was built in RRI. This is the, in those days, you can see this is what's called Pentium 4. And this is the one which was actually fabricated at electronic controls. And this is the data acquisition system. And the whole thing is inside this box, and this is an aluminum box. The very important point here is there should not be any vibrations. And also noise and other things, it will even, small disturbance, because you are thinking about sub-nanometer resolution, So even a Armstrong disturbance will, spoil the image. So you have to keep it in an enclosure like this. And this enclosure with a bungee cord, it's connected to the ceiling. And then this inflated, car tube, and then a granite, block, and kept over a teakwood table. This was bought by C.V. Raman long back, and it really helped us to have this, And so this is the first image about which I am always excited of highly oriented pyrrolitic graphite. So these are all carbon atoms. I will not go into too much of details about whether this is a carbon atom or electron density, because strictly speaking, these are some, what's called a local density of states. So there is not, there's a subtle difference between the two, but you can actually see these carbon atoms, and this is during the forward scan, and this during the records, and you can see the hexagonal pattern here. Okay, and one way of testing whether this is real or not, what you have to do is you have to double the distance, and if you you can see you for the same scan rate, you can see double the number of atoms. And see, this is 4 nanometers, this 2 nanometers, and you can see these are the variations that was corresponding to these lines. So this is the one which really sealed the entire thing, because this is the one highly oriented pyrrolitic graphite is used as a for calibration purposes of scanning tunneling microscope. So this was achieved, in October 1998, if I remember correct, and it was subsequently published, in Current Science, because this is something which I could easily get it published instead of sending it to referees. And we had a good referee here also, but in a foreign journal, it takes much longer time and so many queries. And here, some veteran experimental physicists came and saw that the whole thing was demonstrated, and then it got published, in Current Science, and this is the cover page of Current Science at that time. So, and this is subsequently we could get spectacular images. So this is one of the three-dimensional images of graphite, and this is the gold surface polished with the 50 nanometer alumina. You can see these are alumina surface. If you polish it, you can actually see the gold surface on the mirror. But if you really scan it with STM, you find there are so many roughness here. you can see that there are so many, depressions and asperities, hills and valleys. So this is this is a mirror image. Actually, you can see this is this one. So the mirror image actually confirms whatever you are seeing in the forward scan is something reproduced. So another, important thing about STM is it actually started, making waves initially for about a decade or so. But then AFM came in. When the AFM came in, people suddenly shifted all of them to STM, saying that, oh, STM can only study, conducting surfaces, and it's no good for organic materials and biological materials and all those things. So that's the kind of, not necessarily in India, but anywhere, all and it's much easier to interpret an AFM image and much easier to get a sample of AFM, which I'm going to talk about. There's nothing to really downplay the importance of AFM, because this is really creating a lot of important discoveries. But the only thing is, there is a lot more that can be done with STM. So we proved that STM can be used to study organic materials also. See, for example, these are all imaging of cytochrome. Cytochrome C is, protein, which is responsible for respiratory process. And this is actually, deposited on a surface, of HOPG, and then we imaged it. You can see the individual protein molecules imaged with STM. So it is too much, it is rather premature to, abandon STM and say that, it's not good for, the reason why, you may ask, how organic molecules are there, how, when there is no surface, conducting surface. The reason is simple. You have HOPG, which is conducting, over which you have these organic molecules of a few nanometer. The process of tunneling can happen through the organic molecules also. It is very well known, many of the proteins are actually electronically conducting also. So that is the way in which we could really see, molecules of the order of something like 15 to 20 nanometers. So how the electron hopping through the protein is a different study altogether. It has all been studied, but then not much of studies are there in, using STM. So these are all, over carbon nanotubes. So what we have done is, the carbon nanotubes have been functionalized with cytochrome C, and then we tried to image them, and the cytochrome C molecules got wrapped onto the carbon nanotubes, and you could, you could really see here the, the carbon nanotubes wrapped with the cytochrome C. We could actually see this individual cytochrome C. This was actually published, in Journal of Electrochemistry, Nagaraju, and I'm also the co-author. So this is, this is a myoglobin. So these are all macromolecules which can be imaged. And for this, anchoring is, how do you anchor these proteins onto carbon? The way we have done is to use what is called 4-amino-thiophenol, which is actually aromatic molecule through which electrons can flow and over which this protein is immobilized. So because of that, the tunneling effect, we were able to image over that bed of amino-thiophenol. We have be able to image the protein, and this is a very interesting topic. Those who are studying, interested in biophysics and biochemistry can explore these kind of studies further. So after, immediately after scanning tunneling microscope got recognition and got Nobel Prize in 1986, Gerd Binning thought about, we are tunneling here. Why don't we try to see whether there are any other forces which can actually are effective at that small distances, so that we can make use of the device, any new device, for the purpose of studying the conducting surfaces also. So this was the work which was done by Gerd Binning, who was one of the inventors of scanning tunneling microscope, along with Quate and Gerber. And the same, I mean, in 1986, they invented the atomic force microscope. The atomic force microscope is based on a very interesting, well-known concept of interatomic forces. So this is the famous Leonard-Jones potential curve. You can see when the atoms come together. This also studied in spectroscopy as Morse curve. So when the atoms come together, initially there is a weak attraction, and then the attractive forces increase because of the nucleus and the electrons of the other atom, and then the overlap of electrons. And beyond, and it reaches a potential minimum. And then again, it increases because of the repulsion, because repulsion between the two nucleus, two nuclei. So in that process, there is a repulsion. So this is the equilibrium point. And so why can't we use this kind of attractive force or a repulsive force to see how the forces vary with the distance? Because clearly the forces are dependent on the distance. So if you have a similar tip like STM, and you can have a surface, and if you can measure the forces, and how do you measure forces? The force at that level can be measured using cantilevers. So this is the one which is based on very well-known concept of Hooke's law, So this is something, force is proportional to distance, and the Hooke's law is very well known. This is the analogy of spring balance, So in which you have the cantilever, which is having a very bright surface, and this is the tip. And classically, diamond was used initially, but then now is silicon nitride tips, because it has to be very hard, the tip, because it's going to, scan over the surface, and in the process, it should not get deformed. So, and then over which there will be some platinum or gold coating, and then this will be, laser will be focused on that, and then laser beam will be reflected. And there is called, what's called, quad photodiode. And why quad means, I will just explain it here. See, if you have a quad photodiode, when the tip is positioned at a particular position, laser beam is incident on it, and this is getting reflected, and you can initially adjust it at the center of the photodiode. There are 4 quadrants, split photodiode, and each independently they are the ones which will convert light into electricity potential. So this is the center where it will be 0, and then when there is a small deflection or anything, when there is a change in the position, you will find that, whether here or here, that will be proportional to the deflection. So that's the way it operates. So that's why it is. And this is a very simple, conceptual, diagram. And when, so this is the kind of a tip, you can see the conical, tip. And you have this, it's made of silicon carbide, silicon nitride, and all those things. And the spring constant is 0.1 nanometer or so. So the position sensitivity detector changes the light. Tracks the light beam, and the light beam itself tracks the position of the cantilever. So this is how it operates. So you can see that when the tip, when it is moving like this, it actually moves and follows the surface, profile. Okay, so this is how. And the principle of AFM and STM is different only at the scanner level, but otherwise in the electronics, piezo control, and other data processing, all those things are almost same like in STM. And this is a very initial AFM system that I think that was bought out by digital in those days. So this is the laser beam, and you can see that cantilever, and the deflection photodiode goes to the feedback. So the idea of using a feedback is to same way to make the distance between the tip and the sample constant, and whatever voltage that is the feedback necessary to make that constant is proportional to the distance between the two. Okay, so it has a lot of applications of AFM in biosciences. It can image non-conducting such a biological system, analyze crystals of amino acid, organic monolayers, DNA and RNA analysis. So protein, nucleic acid complex, chromosome, cellular membrane, proteins, peptides. See, all these things, initially when AFM came, there was a lot of excitement, and people started imaging left and right, all these biomolecules, and they were very spectacular images were obtained. And to go into a little more detail about the AFM, there are three modes. One is called the contact mode, where the tip literally touches the sample. This is in the repulsive regime, repulsive forces. And then there is so here it just touches the sample, and you keep that maintained distance between these two constant, and then use the feedback. There's something called non-contact mode. It doesn't really touch the sample, but it actually moves just above the sample. It is mostly in the attractive regime in the Lennard-Jones curve. And it doesn't, so it does. See, the advantage of non-contact mode is, if you're studying biological molecules, here it can be used for semiconductor and other materials. Here, biological, it doesn't really, damage the surface of the biological species. So this is one. But most popular thing is what's called tapping mode. In the tapping mode, the tip is intermittently tapped, and during the tapping, the amplitude changes. Amplitude, the resonance frequency changes, and then the amplitude changes, and that amplitude is tried to be maintained constant. And this is the one which is very popular, because it can actually have a much better way of imaging, and also it doesn't damage the surface because it's not continuously in the contact. So this is what's called tapping mode AFM, and it is used for polymers and soft materials and all those things. So this is how it is. So this is the tapping mode AFM. So non-contact mode is oscillated about resonant frequency at an amplitude of 10 nanometer. It doesn't touch the sample, and constant oscillation amplitude is maintained by feedback. And the forces are actually intramolecular forces are the usual van der Waals forces. It can be also Coulombic forces and magnetic forces and all those things. So this is the STM of cytochrome C enzyme, which was imaged in our laboratory, and same which I showed in STM also. And this is from other laboratories. So you can, this DNA, you can see that, some kind of a helix, this is a protein, and you can see in the DNA, you can see this the one which actually is a very high resolution image. It's a very recent publication, Nature Communication. DNA structure, you can actually see the base pairs and other things. So this is how the AFM has evolved into a very powerful tool to image biomolecules. And also, many of the biophysical studies can also be done with the AFM tip, and what's called the single molecular force spectroscopy. This is a very emerging tool to investigate mechanical properties of biomolecules like proteins and DNA. You can actually attach the tip. All that you have to do is to functionalize the tip with certain molecules with certain functionalities. For example, if you are actually trying to have a tip, the tip can be a gold tip, and then you can actually attach some molecule with a carboxyl group, and you have protein. And if you address a amino group, it will get attracted. So then you can actually pull it out, and then you can actually see how this amino acid group, groups are getting detached. This is how the protein dynamics, unfolding dynamics has been studied. And there are a lot of variants of AFM which are very popular nowadays, because you can do a lot of studies using the AFM just by changing the AFM tip into different, using different materials. and for a particular purpose, you can actually use these things for several studies. The possibilities are immense. One is called, for example, conductive AFM, because usually AFM is used for classically in non-conducting surfaces. You can also use it for, use a conducting AFM. You can actually measure the conductivity of the material, nanomaterials, even organic materials. So you bring the conductive AFM tip close to the sample, and then you can actually measure the current flowing between the tip and the sample, and use this for mapping the conducting and non-conducting regions on a surface. And magnetic force microscopy is used in, for imaging the magnetic domains and to measure the magnetic properties of materials. So this is a magnetic, see, instead of silicon nitride, you use gold here for conducting AFM. Here you use a nickel as a magnetic material tip. And then you can, when you scan the surface, you can actually see which are the regions which are having the kind of magnetic domains. And you can actually magnetic strength and all, you can actually, map the region. So, and similarly, you have electrostatic force dielectric properties of the surfaces, you can measure, because you can actually have a particular charge on the surface by using again some organic material. For example, carboxyl group, when deprotonated, it will have a negative charge, and amino group with a positive charge. So you can actually use those forces, kind of tips. All that you have to use it, tip, you have to functionalize the tip, gold tip or something like that, and functionalize that tip with certain molecules, and the group will have certain charges. And then when you map the surface, which has certain other charges, opposite charge or same charge, you will still be able to get those deflections. So this actually operates with that Coulombic interaction. Then Kelvin force microscope measure the work function. And finally, I would like to tell something about a very, relatively recent development in terms of tip-enhanced Raman force microscopy, because Raman is something which is very dear to me. And, to ally with the AFM and make it much more powerful in studying the molecular characteristics and their properties at the individual molecular level is something very fascinating. So the tip-enhanced Raman scattering actually is a byproduct of what is called surface-enhanced Raman spectroscopy, which was actually discovered about 50 years ago by Martin Fleischmann. But then it evolved over a period of time. See, this Raman spectroscopy provides a very feeble signal. That's how it was till 1974 or something like that. But then a phenomena where certain material with certain refracting index, certain dielectric properties like silver, when it is roughened, has enhanced the Raman's property, Raman spectral strength by several orders of magnitude, sometimes even million times more. Typical example was initially studied was pyridine on silver, electrochemically roughened, silver material. That was there, but there were a lot of work that was going on. And in fact, Raman spectroscopy has become more like a, very handy instrument for forensic studies and other things. They all use the surface enhanced Raman only. And this is being used in even, detection of, narcotics and drugs. And this being very prevalently used in, US airports and other things. That's what I hear. And this is something which was finding a direct application, and also in very important, research studies also. So what it really means is you bring a, AFM tip, cantilever with a tip. If the tip is, for example, silver, which is a very common material used in enhanced Raman, and if you apply a laser light, at that location, the electromagnetic field is enhanced several orders of magnitude. This is due to the surface plasmons which were created on the silver surface. The surface plasmon, localized surface plasmon enhancement, in turn, actually enhances the Raman signal, both in the incident Raman and also the scattered Raman. And that is the one, So if you have nanoparticles, this is the surface plasmons which are created, and that actually. So what you feel with the enhanced field, you can actually address the tip onto a single molecule also. And you can actually, a single molecule, you cannot get a Raman signal in a, classical way, impossible. But when you address this way, you will be able to get a Raman signal at that point in such a way, you can actually, the signal enhanced is of the order of more than 1 million. So that way, you can actually get Raman signals of individual molecules. So finally, I would like to conclude by saying the quote of C.V. Raman: when we want to achieve, whether it be in science or in anything else, we must first learn to use resources we have in plenty. That is our young human beings, of whom at least a third are young. Now I don't know. During Raman's time, it was third of young. Now probably 60%. This is our strength. If they are enthused and if they are instilled with the spirit of adventure, the sleeping giant will wake up and we can conquer the world. So that was the dream of C.V. Raman more than 50 years ago. And I think it should not simply remain as a dream. And many of the people who are youngsters here listening will try to live up to what Raman dreamt of. So thank you very much.
Thank you, sir, for exposing the intricacies of the microscopy,
yes,
STM and AFM. It's a very interesting technical session for us, how it is happening. And how many people are aware of the outcome of these things, the vision of proteins or some other molecules using these kind of techniques. But we haven't known the things, and we are interested to know that your improvisation in this compact type of STM, that's your contribution. We are we proudly hear from you, sir. It's your contribution to the nation and the research institute here. And both these AFM and STM are useful in the life-saving process, especially.
Yeah, I think we have to really explore the unexplored. That's very important. Many times we go by the trend, So my feeling is the STM is something that youngsters can take it up much more vigorously, because that was actually hastily left behind, and people started. Now, after so many years, now there is a lot of potential for STM, and you can learn a lot of quantum physics, there is so much to do. In fact, the recent Nobel Prize in 2025 was for macroscopic quantum phenomena. So macroscopic quantum phenomena is unlike what we saw with the individual electrons. Now it's a collective, millions of electrons at superconducting stage. You can have devices. So it is still, the tunneling is still a fascinating, study, and youngsters have to really explore this further, and this is one which will be truly rewarding. That's what I feel.
Okay, thank you, sir. And we have recorded this. It will be there in our YouTube channel. Your talks and presentations will be as a repository for our students. And sure, we could say that it's an ignitatory moment for our students, just like our C.V. Raman's words. We have the treasure with us, that's the youth, and for them we are conducting these kind of activities.
Yes, and, because C.V. Raman is the role model for all our, scientists, and our youngsters have to read more about him and how he did with the humble, optical, devices which he had to make a Nobel Prize discovery,
Yeah, right. Generally, that's the thing, is that we have to think simple things. We have to consider simple things with scientific and curious observation, right? Then we'll get some kind of hidden secrets or codes there in every phenomena. That's we are getting from here. Normally, the students think about the black hole or like large, huge things, and rather than going that, we have to see what is the micro things there. We have
Exactly. You know, because what we see is something which is much more, in terms of, stars and galaxies, Milky Way and other things. What we are not seeing is something which we really, have to understand more,
Okay, sir. Okay, sir. Thank you. Then before we are going to this question session, we would like to get some kind of reflection from Dr. Jyoti Basu and Dr. Bharati ma'am is there, and we thank them for bringing you to this platform. And welcome.
I should thank, anyway.
Okay, thank you. Jyoti Basu, sir, please. And then after that, the students will ask some questions.
Yes.
Lakshminarayanan, it was a wonderful talk.
Oh, thank you.
Get to know some of the things I didn't know. Okay, and quantum tunneling is something which I'm familiar. I think it started with Josephson Junction. Josephson Junction got the Nobel Prize for his work on, I think not many know it. That is quantum tunneling. Okay, you have the superconducting thing and separated by insulator. And just the current passes through. And you have the DC tunneling and the AC tunneling, something, and it is being used in quantum computing. As a matter of fact, a lot of scanning tunneling microscopy is used in the research, quantum computer research. I think looking at the elements used for the quantum computers, both more STM than AFM. Both are being used in quantum computers. And you have touched on so many things in this brief, very nice technical talk. I'm sure that the students would have picked up few hints from here and there. And I could see some comments coming up. More than anything else, they're curious to know where can we do it. We are coming from institutes which don't have any of these facilities. Whom do we approach to do some STM work or AFM work? And I have seen SEM and transmission electron microscope. We had SEM and TEM, the first place where I worked. But see, when you worked on, I think to everyone here, the other day, maybe a few months back, somebody in Stanford said that, proudly said that he was taken to his process lab where he fabricated a scanning tunneling microscope with his students. I said, Baba, this my friend did it 3 decades ago. So I am so proud to say that. And you're amazing here. I mean, the kind of electronics involved, the kind of, instrumentation is not a joke, right? It needs precision, it needs deep understanding. Then only you can develop something like this. As he rightly said, there was a history of people making their own instruments and then working with to create knowledge. I mean, that's what you did. I mean, you made the STM and you didn't leave it off there. Then you used the STM to study a lot of systems and produce a lot of good papers and contribute to scientific literature. Amazing, yeah. I mean, proud of you. And
it's all due to
due
to my inspiration that I got from people like you.
And whenever we meet, I get excited because I like talking science to people, and you are one of like that. I mean, we can discuss science, okay?
Yes.
And you feel so tiny. I mean, when you look at the nature and the wonders the nature does, I always think that in a leaf plant, the leaf of a plant, so many things are happening here. And
yeah. Yes.
it's amazing the kind of kinetics which is going on there, at the speed it's going on.
Absolutely.
The level, yeah.
You can learn a lot of
Yeah. And
chemistry and
there,
physics also.
there wouldn't be sunlight without quantum tunneling. I think it starts from there.
Yes.
I think quantum
Exactly.
tunneling is the phenomena for sun shining. I don't think we know that.
Yeah.
Okay, great. I mean, that's all what I can say. I don't have the technical expertise to. I mean,
You
comment
talked
on things.
Joseph Junction, and
You've done it well. You've done it
no,
well.
that is the one which actually last year's Nobel Prize is
Yes, I know.
based
Yeah.
on.
Yeah, the moment I saw the Nobel Prize, I was thinking, why years tunneling was done by Josephson? He got a Nobel Prize along with someone else. And now they're doing quantum tunneling at room temperature and semiconductors, macro
macro.
electronics. Microelectronics. Okay, I think Bharati wants to say something.
Really, I enjoyed your lecture, Lakshminarayanan.
Oh, thank you. Thank you.
Yeah, because I didn't have an opportunity to use STM. For our work, we have used SCM extensively.
Yes.
And I think I visited your lab once and seen your instrument.
Yes.
And even in our initial days, you had developed a corrosion monitor, you remember?
Yes.
In our earlier days. Then itself, I
No,
think
actually,
it was
those
a wonder
things-
for us in those days.
No, actually, those are the training, initial training,
Yeah,
which
yeah.
actually sort of helped me
Yeah,
in working on
really.
this electronics.
Yeah, in the 70s, you had developed that from scratch. Then itself, we knew you are for big things and you.
No, I knew very well that at
improved
that point of time, I am no use using these organic chemicals.
Yeah.
No,
I know,
nothing,
but it was-
nothing adverse about it.
Yeah.
But then I thought this was much more fascinating, that's all.
Very good, very good.
Yeah. We are opening
Yeah.
for comments from
Yeah.
others. Sajil,
Yes.
I mean, you can ask anyone else to give
Sir,
any
it's
comment.
time for some questions are there. And Ritik will handle that. Ritik?
Yes, sir. Can you hear me?
Okay, first you introduce yourself and for sir and you can proceed.
Hello, sir. I'm Ritik Srinish. So I'm studying in class 12th of Bharatiya Japan School, Chevayu. So first of all, I would like to thank you, sir, for such an informative and engaging class. And I could get a lot of new information from this class and I enjoyed it a lot. So, sir, can we move on to the question answer session?
Sure.
Okay, sir. So the first question is from Arjun J. His question is, we learned about scanning electron microscopy in our first year of BTech. So what is the major difference between SCM and STM? Also, what is the disadvantage of SCM, which leads to the invention of STM?
So there is a big difference between SEM and scanning electron microscope and the scanning tunneling microscope. The scanning electron microscope, it depends on very high energy electron beam, getting impinged on the sample. So of the order of something like 10 to 30 kilovolt, high energy beam getting incident on the surface. And then the process itself generates what is called secondary electrons and also backscattered electrons. The secondary electrons and backscattered electrons are detected by a electron detector, and then that actually provides you the two-dimensional image of the surface. That you can actually get the two-dimensional image of the surface by impinging the high energy electron beam on the surface. So this is called a scanning electron microscope. Since the beam is scanned over the surface, this is a scanning process. And then the electrons, you can either measure backscattered electron or secondary electron because there are two modes in which you can measure it. And depending upon the intensity of these two, electrons, you will find the image being, used either backscattered or secondary electrons. So these are all emissions from the surface. That is, it's coming out of the surface. by that process. And, this is a very useful tool to image metals and conducting surfaces. But when it comes to non-conducting surfaces, classically scanning electron microscope cannot be imaged because high energy electron beam on a non-conducting surface will actually, deform it, It is not conducting. So especially, when you image that kind of a thing, either it will get incinerated or it will get heated up, it will get distorted. So you will not be able to do anything, and it will not emit the secondary electron or backscattered electron. So you cannot be using SEM for non-conducting surface. Having said that, I would say that there are many modes in which recent times SEM has come. One of them is called the charge-coupled mode, where you can actually, the charges which are not dissipated in a non-conducting surfaces can be actually dissipated using certain methods, and then you can actually image non-conducting surfaces with the low energy beams, like for example, 1 electron, 1 kilo electron, and all those things, electron volt. So that is what SEM is. So the phenomenon of scanning tunneling is totally different. Here we are not dependent on any electron beam getting incident on the surface or any electrons getting generated from the surface. This is purely a phenomena which is outcome of quantum physics, where two conducting surfaces are brought close to a distance of 1 nanometer, and do what you may, there will be overlap of electrons, though they are not touching. So this is a naturally formed electrons on the tip or the surface, depending upon the bias potential, which is flowing into the other one. If the electron is going to the surface electron going to the tip. So either way, there is a current flow, because charge flow is current flow. This current flow is very, very small. It is of the order of nanoamperes, or sometimes sub-nanoamperes, 100 picoamperes or something like that. So this is nothing to do with electron beams, which are very high voltages and very high currents. So, and the advantage of SEM is, STM is, you can actually have a very small current, but you can actually get a 3-dimensional profile of the surface. Whereas there you get 2-dimensional, because the tip is actually going down on a depression, going up on some elevated place. So you can actually get a 3-dimensional profile of the surface. So that is the major difference. And electronics is different. Everything is different here. Yeah. Any further questions?
Yes, sir. Now we have another question from Sophil. So his question is, how can students from institutions with limited facilities still meaningfully engage with research areas like scanning probe microscopy?
Yeah, you can actually, this is a problem, of course. You can't really gloss over it. The thing is, when you want to develop a device, or when you want to work on a very sophisticated instrument, or I should really acknowledge the Raman Research Institute for providing me with all the facilities, and also having confidence in investing in my passion for fabricating an instrument. That's a different thing, because I could get a sufficient funding for doing it. I do agree there is a handicap, but doesn't mean that everybody has to develop a STM. There are many things in which, with the limited resources, one can actually try to develop small devices, as well as some prototypes which are actually be able to demonstrate certain phenomena. For example, quantum tunneling, if you are telling, this is for mapping the surface, one should have that kind of a thing. Why can't you try certain experiments in which you can actually bring the tip and sample in such a position without touching? You can imagine something on your own, how you can manage it, So that way, if you can just connect a very simple multimeter, you will see that current flow. But this needs some additional support from electronics people also. So with the, see, no discipline can exist on its own nowadays, you see. So everything is multidisciplinary. So you have to see the old concept of physics, chemistry, biology, mathematics are all gone. Now everything is dependent on everything else. So if you are a physics student, you can actually engage with physics people with instrumentation background in engineering and try to come out with a device. Why can't we do this? Why can't I see a tunneling phenomena on my own? I'm not going to develop a STM, but how I can get that? So this kind of a thing, if you get engaged in this kind of activity, you will slowly develop. When you get an opportunity to get the funding, when you go independently, you can actually use your expertise and passion for developing instruments. Sorry, that's what maximum I could tell, because limited resources is a problem everywhere, you see. And of course, you have an opportunity to work with some of the laboratories. If you show some initial interest, not just a curiosity, but a demonstrable experience or interest, then definitely some of the laboratories will take you as an as a visiting student or something like that, and you can actually make use of that kind of an opportunity. Yeah.
Okay, sir. Thank you for your informative explanation. So next we have a question from Fabian Firshad. So his question is, if AFM can be used in fuel cell research, including imaging, electrode degradation, etc., how will we operate it in electrochemical environment with possibility of corrosion or tripwire?
Yeah, corrosion is a phenomena which actually is a surface phenomena. So AFM is the right kind of a tool in corrosion research. See, offhand, I cannot come out with any. There are many ways in which you can use for fuel cell electrodes. No doubt about it, because the fuel cell electrodes have gone through several modifications to improve the catalytic activity. Now, one way in which you can use AFM is, see, the nanoparticles of the catalyst, for example, methanol fuel cells, or something like platinum, rhodium, or something like that. Mostly platinum particles. You have platinum, rhodium particles also, and many of these particles are made into nanoparticles, because the platinum loading is one of the major problems in fuel cell research. Where more platinum being used, it becomes more expensive. So the surface to volume ratio of catalyst is very important, So where the surface area is very high for small volume, that's a great thing. So that's why nanoparticles. So you dispersed nanoparticles on a surface like carbon, you can study with AFM. Because if you use, for example, I told you about conducting AFM. So the conductivity will differ from region to region. Wherever the nanoparticles are platinum is embedded, you will find that is having a different conductivity compared to the matrix with carbon. And then you can optimize the surface which is getting exposed to the electrolyte, so that if you have more active surface area on the surface, then you will be in a position to get a more catalytic activity. So some of these things you can actually map with the AFM, especially with the conducting AFM. This what initially, but then there are many ways in which you can use. Only thing is, don't try to use AFM for rough surfaces. It has to be reasonably smooth. If you want to have a rough surfaces image, you have surface profilometers, which can actually see the variations of the micron order. But if you want to really see at a very nanometer scale, you can use AFM, and I would think that conducting AFM is something which probably you can use. And also some nickel particles and other things which are used in some fuel cells, you can actually map it out with magnetic force microscope. So nowadays, AFM itself doesn't come just with AFM. It comes along with all these other cantilevers like MFM, magnetic force, electrostatic force, conducting force microscope. All these things, they come only cantilever you need to change. So that's how you can actually use for magnetic materials. So fuel cell research, it has a lot of potential, and I'm sure there must be hundreds of papers on this. Yeah.
Okay, sir. Thank you. So, sir, the next question is from Adil Prajesh. So, his question is, what is your opinion about future of microscopy? Can we see subatomic and beyond subatomic levels?
No, but why? See, the thing is, as of now, we are seeing only the surface. Surface atoms. You can't use STM to see the atoms in a bulk, or you can't take any surface and then see those atoms. You see, it always goes with a rider. So whatever surface you want to really see, a polycrystalline surface, you can't really see the atoms with STM. It's simply not possible, because polycrystalline materials have different orientations and other things. There is no order at all. Now, if you want to really see even with the STM surface atoms, you need a challenging thing. You need a single crystal atoms, or that's why they use graphite, which is a highly ordered surface, and silicon, something like that. So these are some surfaces on which already atoms are there. Atoms are smooth atoms. But if you really want to see some of these other subatomic particles, you can see them as a phenomena. You can't really magnify them or try to see them like, here also you are only seeing the electron density. STM also, though it is claimed as seeing atoms, because electron density is high around an atom. That's why it is an atom imaging. That's why it's called. But strictly speaking, it shows local density of states. Now, wherever local density of state, electron density is high, and that's what you are imaging. So, if you see whether you can see subatomic particles other than electrons and protons and neutrons, I'm not a particle physicist, and I don't know whether one can literally see them, but the phenomena is already seen, created them. Yeah.
Okay.
Thank you, sir.
Okay,
Thank
sir.
you, sir.
Thank you.
Yeah.
So, sir, the next question is from Shankar. His question is, how long do STM and AFM take to provide readings?
Please repeat it.
How long do STM and AFM take to provide readings?
Yeah, see, STM, one can, in a matter of minutes, depending upon the scan rate, because scan rate itself is based on the sample. So how fast you want to image the sample. See, it's not something that we are in a hurry, so you can actually make this sweep faster. It also depends upon the surface properties. So if you want to get typically about, it will take some HOPG, let us say, it takes about 5 minutes to get an image. And AFM, you can actually get an image of the, at the same time scale. But if you want to image some biological samples, you don't need to really tear through the sample, using very fast scanning and other things. So you use a correct mode. And the imaging itself, whatever modes you use, is again depending upon trial and error. So you try one contact mode, and you see tapping mode, you see non-contact mode, you see which is the one which is giving the best image without damaging the sample, without having artifacts. One of the major problems with all these things is artifacts come in. So artifacts are created by noise, some vibrations and all those things. So all these things, if you take into account, if you are given, let's say, you give a very atomically smooth surface, give me in 5 minutes, if you give me the image, it's not possible. So it may take a day or so, if to be, get a very good image, because you are going to go on trying to get the best image. So the scanning itself is not important. The important thing is the surface, preparation of the surface, and then the optimizing the bias voltage, current, as well as the scan rate, everything. So this goes only by trial and error. So it may take typically about a day or sometimes even a week if you are not able to get a good image. So good image itself is based on many other factors, disturbances and other things. And the sample, how it is formed on the substrate, the stability of it, all those things. So these are all studies actually. It is not, see, many people think you give a sample and you get an image. No, it's not possible. It's not like a typical microscope image, just to put a slide and then see the image and take a photograph. So it's not like that. Yeah.
Okay, sir. Thank you. So that was the last question. I hope everyone cleared the doubts. So thank you all. Thank you. Once again thanks, sir, for such an informative and such a great class. So thank you.
Thank you very much. Oh, thanks a lot for patiently listening and asking very, perceptive questions.
Okay, sir. These questions are our spirit. That's why for them we are sitting and hearing.
It's
not with the number, they're curious minds. And
very interesting questions, I think.
right. We have been here around 1 hour and 45 minutes here, and there was some technical glitches.
Oh, 1 hour 45 minutes. Oh, my goodness.
Right. Then, okay, thank you, sir, for your words to our children. And
thank you so much for bringing me here, and I will be in a position to.
Then the official vote of thanks will be by Arjun. Arjun, are you there?
Yes, I am.
Arjun, please introduce yourself, and he will make the official vote of thanks for this session.
Okay, sir. Good evening, everyone. I am Arjun. I am a BTech student at NSSE Palakkad. So, on behalf of the US Space Club, I extend my heartfelt gratitude to each one of you for being a part of our 84th webinar session. It's been a truly engaging session that took us through an inspiring journey and motivated the young minds gathered here. First and foremost, we are really grateful to our speaker, Lakshminarayanan sir, for his captivating talk. For Lakshminarayanan sir, research is about rigor, not buzzwords. He is driven to make advanced physics and instrumentation approachable for students who want to go beyond textbook learning and exam-focused coaching. Through his work at Raman Research Institute and beyond, he has helped turn curious questions into real experiments and impactful scientific contributions rather than untested ideas left on paper. We are also deeply grateful to our founder and mentor, Sri E.K. Kutty, whose vision and passion continue to guide the the US Space Club to reach new heights. A special thanks to our moderator, Sri Shaji UK, for smoothly coordinating this session and ensuring a seamless flow of ideas and interaction. And of course, a big thank you to all the participants who joined us today. Your enthusiasm, questions, and passion for learning are what make the event like this so impactful. With that, we conclude the session. Thank you and have a great evening. Thank you, sir.
Thank you so much.
Thank you, Arjun. Okay, we'll meet again, sir. And we request your support to these kind of sessions. And
sure. I will try to, rope in somebody else also.
That would be a great thing for us.
Yes, thank you.
Thank you very much. Okay.
Thank you. I think muted, Jyoti, you have muted the phone. You have to unmute.
I said thank you.
Yeah, thank you.
We'll meet sometime.
Thank you so much for bringing me to this forum.
That's okay. It's my pleasure. Okay, bye.
Okay, sir. Thank you, sir.
Yeah.
Thank you. Thank you.
Bye. Say hi to your wife also.
Okay, sir.
Bye.
Bye.
Bye, Shadil.
Okay, sir. Thank you. Thank you, sir.